In this lesson, we're going to look at correlation and chi-square. These are two fairly common statistics, so if you obtain an understanding of them, I think it'll help you understand some of what you see reported in journal articles, as they're fairly often used and common. So correlation is an inferential statistical test used to examine the relationship between two variables. We went over in last lesson how we sort of cut off or use a threshold as to whether something is statistically significant or not. And that's an alpha level of 0.05. So when you obtain a correlational statistic, the mechanism for which you will decide if it is significant, if the relationship between variables is significant, is using an alpha level of 0.05 as your cutoff. So a correlation looks at relationships between variables, but it cannot establish cause and effect. If you think about it, there is probably a very high correlation between ice cream consumption and drownings at the beach. The two probably reliably, co-occur together. Was your mother right? Was eating right before swimming something deadly and dangerous? Maybe, I don't know. But probably the relationship between ice cream consumption and drownings at the beach has more to do with temperature. That on hotter days, people are more likely to be in the water, and they're also more likely to consume more ice cream. This is a relationship that is really hinged on a third variable. So X can be related to Y. Ice cream consumption can be related to going into the water, and going into the water can be related to ice cream consumption, but both are probably bolstered and are carried by a relationship to a third variable. And the thing about correlation is you can never necessarily know whether you've covered all those third variables. So we always assume that correlation does not equal causation, but it does tell us whether two things are reliably related. If you see A, you will probably see B. A correlation also has to describe a linear relationship, and we'll talk about this a little bit more in the lesson. A correlation statistic basically ranges from 1 to -1. A 1 is a perfect positive relationship, a -1 is a perfect negative relationship, and 0 is in the middle, indicating no relationship at all between the two variables. The number that you get, ranging from 1 to -1, can tell you two pieces of information. The first is the direction of the relationship. This scatter plot depicts a negative correlation. With a negative correlation, the two variables do co-occur together, but they co-occur in an inverse relationship. That is, as values of one go up, values of the other go down. And you can see this depicted in this particular graph. You can also have a positive correlation, in which as values of one are increasing, values of the other are increasing, or vice versa. When you want to decide whether a correlation statistic is positive or negative, you just have to look at the sign. So if there's a negative sign, it depicts a negative correlation. If there's a positive sign, it depicts a positive correlation. An example of a positive relationship might be something like studying time and grades. You would expect that the more time you spend studying, the higher the grade you will earn in a course. With a negative relationship, you might think of it as something like the reason why we don't necessarily prefer very, very old people driving, right? We assume that there's a relationship between age and reaction time. As you get older, your reaction time will slow down and you'll be less able to respond to something. So in that case, as age is increasing, reaction time is decreasing. The other piece of information that a correlation statistic can give you is the strength of a relationship. So by looking at the actual number of the correlation statistic, you can determine whether it's a strong, moderate, or weak correlation. You would do that by looking at how close it is to 1 on either pole, so either negative or positive. In terms of the correlation statistic and the strength of the correlation, a loose guideline is that in and around 0.80 and above is considered a strong correlation, and between 0.40 and 0.80 is considered a moderate correlation, and 0.40 and above would be verbally described as a weak correlation. So take a look at these correlations and decide which correlation do you think is the strongest. Were you tempted by the 0.50 as compared to the -0.80? In fact, -0.80, -0.80, would be a stronger correlation than 0.50. The negative in a correlation statistic does not connotate positive and negative numbers like you might have used in math, and that being negative numbers are less in value than positive numbers. The positive and negative connotates direction of the relationship. So in fact, -0.80 is closer to -1. Closer to 1, stronger relationship. Which one do you think is the weakest correlation? Hopefully you picked 0.10. 0.10 is closest to 0. Whichever number is closest to 0 is a weaker correlation. So 0.10 would be weaker than -0.20. The other thing about correlation is, to keep in mind that we talked about before, is that correlation is sort of hinged on an assumption that the relationship between variables is linear. If the relationship between variables is not linear, correlation is not going to be the best statistic to test it because it will underestimate that relationship. So here I have an example of a curvilinear relationship. That is, values initially are increasing, they sort of plateau, and then values are sort of decreasing on the other end. I actually did find this in one of my own studies. The study was looking at rates of sexual coercion and alcohol use. So what was found was that as the amount of alcohol use was increasing, rates of sexual coercion in couples was going up, but then it sort of plateaued, and as rates of alcohol use kept going up, rates of sexual coercion started going down. So it was actually a curvilinear relationship. Why? Well, we speculated that that was because at a certain amount of alcohol use, cognitive and physical functions decline. And so with those declines, we assume that there is also a decline in sexual coercion within the couples. So there's a sort of range where you're at risk, and then actually at excessively high levels of alcohol use, the person is more cognitively and physically impaired, possibly ready to pass out, and so you see actually less of it. The other thing you have to be careful of is restriction of range. And restriction of range is if you set about to do a study and you only sample a subset of a particular relationship, you're going to also underestimate the relationship between the two variables. For instance, if you were interested in women's perceptions of adequacy of daycare and you went to a community, say like in Westchester, that was fairly well off, and only asked within that community, that's restricting the range of potential answers on that question. The reason why it would then maybe underestimate the relationship is all of those people who are sort of upper middle class would be giving much the same answer, and they might find it, more adequate than not. This answer might be different than if you sampled communities that had lower income or maybe even higher income. You're only getting one subset of range of what values could be on that potential variable. And so in the end, it might look like that there's no relationship between the two variables, when in fact that there are if you sampled the full range of potential scores on those variables. So when you're doing correlation, just be sure that you are aware of the potential for curvilinear relationships and restriction of range, both which will underestimate the correlational value or relationship between two variables, or in the case of curvilinear relationship, it's really not the best way to assess that relationship. The other statistic that is also fairly common and falls under non-parametric tests is chi-square. Chi-square is used when variables are nominal. So variables have to be along the lines of yes, no, male, female, Democrat, Republican. And basically what a chi-square does is it calculates the discrepancy between the observed frequencies, what you actually got for data, and the expected frequencies, what you would expect based on probability for the same categories. So for instance, if you were to toss a coin, what is the probability that that coin will come up heads? Hopefully you guessed 50%, right? 50% heads, 50% tails. Now, if you have a coin and you want to decide whether that coin has been tampered with in some way, whether it's a good coin or whether it's a trick coin in some way, you're going to flip the coin many, many times, and you're going to observe how many times you get heads and how many times you get tails. In theory, it should be 50-50, in and around. 50% heads, 50% tails, plus or minus a little bit. Then you would calculate what would be the expected frequencies for those categories. And you would see, do your observed counts differ from what you would expect based on probability alone? And what ends up happening is that the distribution of a chi-square is always going to be positively skewed, because if your observed counts and your expected counts are exactly the same, you will end up with 0, right? So if you expected 50% and you actually got 50%, 50% minus 50% is 0. What ends up happening is that the more your expected counts and your observed counts deviate from one another, the larger the chi-square statistic is going to be, and when it's at very, very high and large values, this is the area in which you would say, oh, there's a statistically significant difference here. That, if you're looking at men and women and propensity to vote Republican and Democrat, if you get one statistic that varies greatly, observed from expected, you would get a very large chi-square value, and you would say, oh, something special is going on there. There's probably some difference between groups. The other issue is, with a chi-square test, your categories have to be independent of each other. So a person cannot be in the same category more than once. With a coin, it's either heads or tails. The person answers, do you vote Republican or Democrat? Yes or no. So they cannot be both Republican and Democrat at the same time. They cannot be answering both yes and no at the same time. So those categories have to be independent of each other.